All right. So, hello everyone, and welcome to another session of the Fintech Firesides. My name is Professor Ishaan Srivastava, and today we have an absolutely wonderful guest today, Al Lopez. Now, I'm going to quickly begin with a rather lengthy bio of Al. But Al, welcome to the Fintech Firesides. So here we are. Al is a senior software professional with over 50 years of international industry experience. He was drawn into computer programming at a very early age by a cousin he admired who was a COBOL programmer at an insurance company in New York City. While still in high school, he took a part-time job as a key punch operator in a data center where he quickly gained hand-on experience in programming and operating mechanical tabulating machines like the IBM 407. From there, he went on to the Pratt Institute, where in 1973, he earned a Bachelor of Science in Computer Science. He's always had a keen interest in technological advances and have refined the computer industry throughout his career. He considers himself fortunate to have witnessed and gained first-hand working experience in several transitions as the computer industry evolved from batch processing onto mainframes to time-sharing systems, through the rise of microcomputers to the introduction of personal computing and high-end computing graphic workstations. Connected via high-speed networks, the emergence of the internet, cloud computing, and SaaS applications, and now the rapid advances in artificial intelligence and the dawn of quantum computing. Al is currently the Chief Product Officer at WhoPlusYou Inc., a private software product company that designs technology solutions architecture and develops and operates the software platform which powers TMU's Magnet Network, a digital community workforce and economic development system. Al, welcome to the Fintech Firesides. We're so grateful to have you here.
Thank you, Ishaan, and thanks for that very long introduction. I guess when you've had these many years of experience in the industry, it's hard to kind of summarize it a little more succinctly, but I hope we didn't take up too much of the seminar with that.
Not
That
at
was
all,
quite
not at
nice.
all.
Yeah. But it's a
Okay,
pleasure to be here. Thank you.
awesome. So, I just to start off, I'd love to learn to hear about the evolutions that you've experienced in computing, how they've changed the ways in which you worked, and what you see as the next evolution that we're going to experience in the near future.
Yeah, certainly. As you mentioned earlier in the intro, I started out when I was in high school. I was looking for a part-time job, and at that time, you'd go to the classified section of the newspaper, and there were pages upon pages of key punch operators. So there was a place in my neighborhood called the Institute of Computer Technology. They taught key punch courses. I went there. I learned how to be a key punch operator. And for those of you who might not uh, know what that is, at the time, this was in 1966, right? You would punch holes in cards that were about 5 inches by 7 inches in size and had 80 columns by 12 rows of alphanumeric information that was represented by the holes that were punched by this machine. And those cards were read by the computer equipment of the day. And I took that course. They ended up hiring me, and then I learned how to operate an IBM 407 tabulating machine. And that was one of the first machines that I ever programmed. And basically, it's an electromechanical arithmetic calculator about the size of a small car. So the way that you programmed it was that you had a plug board into which you plug cables. Much like if you've ever seen movies with operators plugging cables into the switchboards, sort of like that. But it was a smaller board, 3 foot by 1 foot, and by plugging the cables in, you could tell it to take the input from here and add it to that other input, and then take that output and put it out to the printer and so on. And then after you plugged all these cables into it, which turned out to be a rat's nest of cables, it was really hard to figure out what was going on if it was a complicated set of operations. And then you plugged that board into the machine and pushed it up against the bed of nails, turned it on, and it would start reading those cards, processing the data, and printing out these listings on endless reams of listing paper, which had those holes on the sides, on the left and the right for actor in the printer to push the paper up through the printer. And I ended up programming and operating that machine, as a job. Now, at the time, people, I think the person who taught me and myself were the only two people in the data center who knew how to operate that machine. And what I witnessed throughout my career in the computer industry is that all of the transitions in the industry kept democratizing access to computing resources more and more. And that's what I've seen. And in fact, that's what I'm really seeing now, even to a much larger extent with AI. So I wanted to take you very quickly through how I saw that those transitions unfold, right? From programming these tabulating machines, I went on to learning how to program mainframes. And at the time, you had to again punch your program into cards, put the cards in a tray, go down to the data center, hand it over to the operator. They would run your program. You'd come back a couple of hours later, sometimes to find out you'd made a typo and you had to change one column in one card and replace that card and then go again, right? And other people, of course, also had programs that they would run and they would bring their data down and cards that were called job control language, JCL, that would run big payroll and billing programs and process all that data. But at the time, in the early stages of this period, they would run those programs one at a time. It was called batch mode, right? So, the access was not all that great. You got a lot of things done, but you had to wait and you had to wait your turn. Then time sharing came along, and I found myself in a room full of people on terminals. Some of them would just type out on paper, others had screens, but still, what you got was lines of text that you use to interface with the computer. And these are time-sharing operating systems. And now I could program by typing my program in through the terminal and running my program, and I would get a slice of time, along with all the other people in the room. And other people who had an account on the time-sharing machine could go in and run their programs, and they could run a number of professional programs. But now, if you see the difference between mainframes and batch mode and time sharing, what happened? More people could access the computer. More people had the ability to run more applications and a wider breadth of access. But still, you had to be knowledgeable enough to understand those cryptic commands that you have to give to the computer, right? There were command lines. There were no windows, no graphical user interface, none of that stuff. So there was still a limited number of people really, who could operate even in the time sharing environment. Now, in the 70s and 80s, the world changed in a big way. I remember Atari came out with a little hobbyist computer. I got one of those. You're smiling like I bet you had one, right? Or you know about it, right?
I know about it. I've seen a few in
Yeah.
museums.
I think mine is still in the basement in a box somewhere. And whenever I mention that to people, they said, you should bring it up and see if you can still get it to run after all these years, right? From the 60s, from the 70s and 80s. And then Apple II came out with programs like VisiCalc. So that was one of the early spreadsheet programs. Then the IBM PCs came out in addition to VisiCalc with Lotus 123 and Excel. So spreadsheets really began to make an appearance. Later, the Macintosh came out in 1984, if you remember the big Lemmings commercial that Apple did at the Super Bowl for the Mac. And even before that, they had a computer called the Lisa. And they introduced a graphical user interface with Windows and a mouse. And what happened? Now, more people were able to run and access computing resources, right? So you had many more professionals. I think accountants probably moved from mechanical calculators on their desk that they had to pull a lever and crank the tape and or crank the paper up and all of that to spreadsheets. Then Apple introduced a laser printer that ran a PostScript protocol, which enabled you to have a plethora of different fonts, and you could format documents, and that ushered in the era of desktop publishing. So now you had even more people who, because of PCs, were able to do things, like applications like spreadsheets and desktop publishing and printing documents and so on. So democratization really started taking hold at that stage. Later in the 70s and 80s, uh, because PCs were limited, we saw the introduction of workstations, and they were capable of running complex 3D graphics applications and so on. We also saw the internet, software as a service, and now what you had was even more professionals, engineers, designers, being able to access the power of these machines connected on the internet where they could access more resources. Some of the applications like the word processing applications became more WYSIWYG. What you see is what you get. It became easier for more people to use these systems. Graphic artists could go in and manipulate images. Much broader democratization, right? Still, to do the sophisticated work on these machines, even on these workstations and PCs, like accounting, tax preparation, engineering, graphic design, and so on, you still had to become proficient in the use of powerful applications. And you had to learn how to use things like TurboTax or QuickBooks or AutoCAD for 3D or Photoshop or Illustrator. So not everyone could use those tools, right? You had to really make that investment and be able to acquire those skills and that proficiency to use these applications. Now, enter AI and large language models. And this is where this is all leading, right, in terms of democratization. Now, if you can instruct or prompt an AI model in a natural language, all right, in the way that you speak to people, you don't have to be a programmer. You don't have to be an expert Photoshop user, for example, to use and access the incredible power of these models and of the servers that they run on. So replacing a background in a photo, for example, is something you can do with an AI model simply by asking it to do that, rather than having to know how to use an application like Photoshop. So that's sort of how I saw the democratization grow bigger and bigger and bigger over the 50 years that I've been in this industry.
God, that is absolutely spectacular, Al. Thank you for letting us go through that.
Mhm.
Um, Now, you didn't mention AI, and when we're talking about AI, the common perception is that AI, talking to AI essentially is like asking a wish of a genie. You have to be rather particular with the words that you use with that genie. So there are a lot of references these days to something either being powered by AI or optimized for AI. I've seen mobile screen protectors that have been
Mhm.
advertised to be optimized for AI, whatever that's supposed to mean. What do you think?
Yeah.
How would you define AI?
Okay, so here, Ishan, I'd like to take a little bit of time talking about AI, but also the evolution of AI over time, right? Because in the topic of AI, there have been a couple of times where there was a lot of hype and then disillusionment, and those were called AI winters, right? And that happened a couple of times. But I think now it's different. And in order to really understand why it's different, I'd like to take you through how the technology has evolved and changed, right? The term artificial intelligence has been around for like 70 years. And it was coined in 1956 by John McCarthy, who was a cognitive and computer scientist at a Dartmouth conference on how machines could exhibit human intelligence. Even before that, Alan Turing, was an amazing mathematician and computer scientist. He was known for helping break the German Enigma code in World War II. And many of you may have seen a great movie about him called The Imitation Game. Um, he proposed, what came to be known as the Turing test, in a paper that he wrote on computing machinery and intelligence. And what he asked in that paper was, can a machine imitate a human so well that a human can't tell the difference, right, between talking to a machine and talking to a human? And that came to be known in the industry as the Turing test. Now, the way the test is set up, you have a human judge, and then you have a human respondent, and you have a machine respondent. And the judge asks questions, typing through text, right, of both respondents, both the human and the machine. And now, if at the end of that session, and they usually go through a number of different questions and several minutes, if at the end of that session the judge, the human judge, can't tell the difference between the human and the machine, then the machine is said to have passed the Turing test, right? Now, I read in Live Science just a couple of months ago that there was a study conducted where, and the paper that was submitted, I think, is yet to be peer reviewed, right? But it does say that they conducted these tests with a number of students, I think, from University of San Diego, and it was a three-way Turing test, the way that I just described. And in 73% of the time, people thought the machine was the human. So even more than the actual human, all right? So, you could say based on this that it passed the Turing test, but at least what you can say that it opens a new debate about how close are we to passing the Turing test in practice, right? Because that was a test condition. But how close are we in the real world when we interact with AI? All right. So let's go back now, in that context and look at some of the developments that happened over time. In 1996, there was a search engine called Ask Jeeves. And I don't know, do you remember? If you remember it, it had that little butler icon, right? Jeeves was a butler.
Yep.
And it was just a search engine. I think now it's called Ask.com. And it tried to set itself apart from other search engines by allowing you to ask questions in a natural language, right? So you might think, oh, wow, that's like ChatGPT, right? You can talk to it in a natural language. Well, it certainly wasn't implemented like today's LLMs. It was based on parsing the questions, identifying key terms and patterns, and then it would return curated answers. All right. So, it was more like looking up based on what you typed, looking up the answers that had been curated into it, and then providing that as a response, right? So, it certainly wouldn't have passed the Turing test at that time. Now, one of the big developments that stunned the world was when Deep Blue developed a chess playing program that ran on a supercomputer, an IBM supercomputer, and it beat Garry Kasparov in 1997. And Garry Kasparov was a grandmaster, a chess champion. No one thought that a machine could ever beat a human at chess. And this was done through a lot of sophisticated programming, which was fine-tuned by grandmasters that worked with the people that developed the program. Like I said, it ran on a supercomputer that could evaluate like 200 million moves per second, although it had very sophisticated pruning techniques, so it didn't have to check every possible combination and so on. And it really won by virtue of the sophistication of the program and brute force, the power of the supercomputer. What's important about it is that it was more of designed to only play chess. It was not generalizable, right? So it was a chess playing system or program, very sophisticated, very capable, obviously, if it could beat a grandmaster, but not generalizable. Now, in terms of what we're seeing today, we are seeing a lot of general application and the ability for the systems today to do a lot of varied and diverse kinds of things. In the early 2000s, we saw the emergence of machine learning. All right, and this is a form of AI because these systems were programmed to learn from the behavior of the people that it observed. And here you saw them in e-commerce applications, right? And what they would do is based on the usage patterns, of the people that were on the e-commerce site, they were able to make recommendations. And you've probably seen this in e-commerce where it says, hey, people like you also purchase these products. And then it lists the other products, right? To see if you're interested in these other things. Well, that is considered a form of narrow AI, okay? It's not generalizable, like what I'm going to talk about a little bit later, but it is a form of AI because the system learned about the usage patterns and how to make recommendations based on that. Now, here's where I want to spend a little bit of time and give you, more insight into why is today different. What's happened that has made AI explode in a sense in terms of how it functions today and differently than even Deep Blue or Ask Jeeves or even the machine learning recommendation engines. Well, the major breakthrough is something called deep learning and artificial neural networks. Okay. And artificial neural networks are inspired by what we know of how our brains work, which are biological neural networks. Right? We have neurons, we have synapses, and they form connections. And as we learn, those connections are further established, in our brains. Right? So the artificial neural networks are a system that was inspired by the brain. It's not a replica of the way our brain works because there's still a lot of things we don't know, about exactly how it works. But it was inspired by the fact that, we have neurons and synapses and connections. And I think it's really useful to understand how a neural network is constructed, what it looks like, in a virtual sense, right? Because we're not talking about a piece of hardware here. We're talking about something that lives virtually in the memory of the machine. Now, I'm not an AI or data scientist, right? So my knowledge about this really comes from the outside looking in. And I'm going to keep it at a very basic level without getting too much into the weeds and far beyond my depth. Okay, you're not talking to the people that that built systems like ChatGPT here, but from my research and study of this subject, I can share with you, some of the understanding of how this works. So let's start by building a mental model of a neural network. And I'm going to use some physical analogies, but remember, we're not talking about a piece of hardware here, right? We're talking about a program and memory and things that function in the computer. All right, so for a neural network, let's start with a rectangular picture frame, like the kind that you can get at the dollar store that you're going to put a picture in, right? Except that inside this picture frame is a matrix containing multiple rows and columns of neurons, artificial neurons, right? Now picture that you stack these picture frames together from left to right, all right? And you have maybe, a few picture frames stacked from left to right. But let's not call them picture frames. Let's call them layers. All right. So now we're using a little bit of the terminology behind neural networking. Right. So now you have these layers of neurons that are arranged as matrices on each one of these layers. What comes to mind for me when I picture this is, have you ever seen like beekeepers when they have these boxes and they pull out these,
Yeah,
and I think they
individual
pull them out
sheets,
to,
right? Yeah.
yeah, they pull
Hmm.
them out to harvest the honey, right? And then they put
Hmm.
them back in.
Hmm.
It's sort of like that. You can almost picture a box full of these frames, right? So it's a set of layers that are arranged horizontally from left to right. And now, for the purpose of this illustration, we'll use the notion of a densely connected network. All right, not all neural networks are densely connected, but what that means is imagine that each neuron in one layer is connected to all the neurons in the other layer, right? So you have on each one of these layers, you have a matrix, n by m neurons, artificial neurons, and each one is connected to all the neurons in the next layer. Okay. Now, the important thing here is, and that goes on from layer to layer, they're all connected that way. This would be called a fully connected, dense network. And like I said, not all of them are built that way. Now, what's really important to understand here is that each one of those connections between neurons has a value. Okay, and that value is called a weight. And why is it called a weight? Because each neuron that is receiving input from all the other neurons in the previous layer, right? their value, the value of that neuron is going to be influenced, right, by the values that are coming from all these other neurons. And what you want to be able to do is say some neurons are going to have more weight than other neurons in terms of that influence, right? So some neurons are going to heavily influence the value of the receiving neuron, and other neurons are going to lightly influence, the value that that neuron is going to get, right? So it's kind of a weighted average that determines, plus a few other things that I won't go into, that determines the value of each neuron based on the inputs from the previous layer, okay? So now let's talk about how you train this construct, this entity, right? For that, you need training data. And what you do is you pass the training data from the leftmost, that's the input layer, and it goes through all what are called the hidden layers in between. And at the end is the output layer that gives you the answer. Okay. Now, what do you need for that? You need a lot of labeled training data. So let's take the example of a network that is being designed to, or being taught to differentiate cats from dogs, images of cats from dogs. All right. These kind of networks that work with images are called convolutional neural networks because of the way that they scan the image and pull out the pixel values and all that stuff. But we don't need to go into that level of detail. So you feed it a picture of a cat, and it goes through the network. And at first, the network, those values are all kind of random. They're not. It hasn't learned anything, right? So what comes out the other end is like totally, unreliable. So the network says, I think this is a dog, right? That's the answer it gets. And because you have label data, you can tell it, no, this is a cat. So what the network does is working backwards, it resets the values of all those weights. It adjusts all of those values all the way back, all right? So that the next time that it sees an image like that, there's a higher probability that it's going to think it's a cat, that it's going to get the right answer. And then you do this hundreds of thousands and even millions of times. And the more training data you feed it, and the more it realigns and resets its weights, the better it gets at predicting whether this is a cat or whether it's a dog, until it gets very reliable at doing that. Okay. Now, at this point, you've trained the network. The weights are fixed and they're locked. All right. This thing is now locked and loaded. The weights are not going to change anymore. The training is done. Then you feed it test data to see how well it does. And test data consists of images it's never seen before, images of cats and dogs that were not in the training data. All right. So now you're really seeing, because the key thing to realize here is that the neural network is not memorizing these images in the training data. All right. Those images are gone. What it's doing is it's extracting what's called latent variables or latent content from those images and saying, what are the lines and shapes and features and textures that are in these images, that when they come together this way, it's a cat. And when they come together this other way, it's a dog, right? And I've set my weights so that my layers and my neurons are able to give me the right answer, that when you have these features, this set of features coming together in this way, I can predict that this is a dog and get the right answer, all right? So I know that was a bit of a lengthy discussion, but I really wanted to spend a bit of time on, this whole notion of how a neural network works, because it's so central to why AI, is taking off, and to the promise that AI holds, right? It's not like the Big Blue program. It's not like the machine learning programs. This is something really, really different. Now, there's a lot more to the way they work. You could get into a lot of technical details. It's a term called back propagation, which is what I described, working backwards, resetting the weights, their activation functions. There's some calculus operations that are performed to determine how to change the weights, whether to crank them up or crank them down. between neurons and so on. And there are some wonderful videos, on YouTube if you really wanted to get a clear explanation of that.
Mhm.
Now, just to give you a little bit of contrast or an idea, frontier models today, and these are models that are pushing the envelope. Okay, so the big neural network-based deep learning models today have hundreds of layers, millions of neurons, and the large ones have over a trillion parameters, meaning weights or dials. The weights are parameters. There's also some other parameters that I didn't mention, but they're over a trillion. One of them has, I think, 1.76 trillion parameters that it can adjust as it trains, and it trains on voluminous amounts of data, right? So these are mind-blowing constructs, right, that are running on these servers in order to answer your prompt, okay? Just to put it into a little bit of perspective, and again, by means of comparison, not an apples to apples comparison, our human brain has estimated around 86 billion neurons, right? So these models have millions of neurons. Our human brain has 86 billion neurons. And they're each connected to about up to 10,000 other neurons. And the conservative estimate for the number of connections that are actually used by the brain, which is lower than the total number of connections that it could establish, right, is about 100 to 150 trillion. All right. The brain is quite an instrument that we have in our heads. And Like I said, it's not an apples to apples comparison, but because the neural networks are not a replica of the brain, they're only inspired by what we know about the brain. All right, but that's just to put it into perspective. Now, okay, so now you have neural networks and deep learning. So what? What have they been able to accomplish? Well, are you familiar with the game of Go?
Yes, I am.
Yeah,
Yep.
yeah,
Hmm.
Chinese game developed in
Hmm.
China, but also played throughout Asia.
Hmm.
Um, it's been around for 2,500 years, and it's a game board with 19 by 19 squares. It turns out there's 2.1 times 10 to the 170th power possible states of that board, and which is estimated to be greater than the number of stars or even the number of atoms in the observable universe. That's how big that number is, right? So imagine trying to develop a program like Deep Blue to try to beat somebody at Go, right? Doesn't scale. Um, but AlphaGo uh, in 2016 beat Lee Sedol, Sadol, 4 games to 1, and he was a Dan 9 ranked world champion in the game of Go. No one thought that a machine could beat and at such a complicated game, at such an involved game, right? A human champion. How did it do it? Well, first of all, it learned how to play by studying a very large number of games played by human experts, right? So as it watched these games, it set all these weights and all these values within all these layers of neurons to understand how the game is played. Once it learned how to play the game, all right, now I'm using the word learning here because it's still in learning mode, right? Once it learned how to play the game, then it played against itself millions and millions of times using something called reinforcement learning. And what that is every time I make a move that leads to a winning game, I reward myself. And if I don't, if I make a move that leads to a losing game, then I penalize myself, right? And of course, the network is always trying to achieve a reward, right? It strives to get a reward. So it starts building up that understanding of, well, I don't know if understanding would be the right word, but it starts building up a set of patterns for which it understands what board states have the highest probability of winning, all right, and what the best next move would be given a given board state in order to get to another state that has a high probability of winning. All right. And that's how it works. That's how it learned how to play Go. And it taught itself, well, through playing itself, using reinforcement learning, how it established these patterns. Now, in game two, move 37, and this is among the Go community. If you mention game two, move 37, they'll all, probably know what you mean. Uh, it made a move that completely perplexed not only Lee Sodal, but all of the gallery of expert observers. They thought that AlphaGo had lost its mind, metaphorically, right? They said, what is it doing? We've never seen a move like this. It was so unorthodox. They thought this thing is out of control, it's going to lose. Well, it turned out that it won in a very unorthodox game, uh, in a way that stunned everybody. It was a move that had never been seen before in the game of Go, and it was executed by the AlphaGo program. There is a movie on Netflix called AlphaGo the Movie. And it's a documentary of all of this. And if you're really interested in that, I would really recommend that you see it. Now, about this time, you know how I said that the neural network, when it was learning or training on all those pictures of cats and dogs, it was capturing the essence, if you will, the shapes, the textures, the patterns, and so on, so that it could recognize whether it was a cat or a dog. If these things come together this way, it's a cat. If they come together this way, it's a dog. Well, at about this time, they learned how to reconstruct images from that data. Right? So if you said, make me a picture of a black cat with green eyes, it had the features and the textures and shapes and so on that it would be able to make that picture, and that's generative AI. Okay, this is, text to image, right? And it went even further because then they learned how to say, make it smile and have it turn to the right. All right, and these things were called variable autoencoders in the jargon of AI, because it could vary elements of that construct of that cat to make it smile and to have it turn its head to the right and so on. So this was kind of the beginnings of generative AI, but the big uh, breakthrough that happened around 2018 was something called the transformer-based language models. And what they did was they implemented an attention mechanism that pays attention to the context in which each word is being used. So, for example, if it sees the word spring in your prompt, is that a natural water source in the forest, a spring? Is it a mechanical spring, like in your car? Or is it the season spring? Which one are you talking about? Well, through this transformer architecture and the attention mechanism, it's able to establish sort of the meaning of these terms. They're called tokens, within the system, based on the context in which they appear. And this led to the systems like ChatGPT and DALL-E, text-to-text generation, text-to-image generation, and so on, that really made it possible for you to talk to them and for them to talk back to you, in a very very complete and full manner, right? Then after that came reasoning models. If you ask an LLM a question, it might give you the first answer, but now the reasoning models start to go through a bunch of different reasoning paths, and then it tries to pick the best one rather than just give you the first answer it comes up with. And they use something called reinforcement learning with human feedback. If you've ever gone to ChatGPT and it gives you two responses and it says, which one do you prefer? I don't know if you've seen that, but some of the LLMs will ask you to pick between the two. You're basically witnessing reinforcement learning with human feedback. You're the human feedback. You're telling it, I prefer this one, and it's sort of capturing that information to make those decisions later. Um, Now, the two, the latest thing before we get into agentic AI is multimodal models. So these models are able to understand not only text, but images and audio and video. And they're able to extract information from those forms, from those modalities that go into the model. So if you give it a picture of a cat or you give it the word cat, once it's in the model, it's a cat. It doesn't matter whether it came from a picture or a word or text, right? And then it can process what it needs to in that context. Um, so, when you think about all of these things going on, You can think about these large neural networks running on all of these servers, doing all of this processing, all of these neurons, data propagating from left to right through these forward, feed forward systems to get you the answer you're looking for. Now, what's developing now, which is the next stage, is agentic AI. And I think maybe we'll touch on that. If we have time, we'll touch on that a little bit later. I see that we're already at 10:42, so this is probably going to go a bit longer than an hour.
I think it's
I'll
warranted.
try to be more concise in some of the other
Oh,
answers, but
no, no,
this is
please
more
don't. I
important.
think it's far more warranted that we have another session to go further into the details of agentic AI. But from what were you talking about so far about neural networks and how they tend to work? There is a sort of a doom and gloom image that's going around that neural networks essentially are forming sort of a black box, so that you don't really understand the workings behind it. Because, like you said, the nodal weightages that are being assigned within it, the larger the neural network grows, the harder it becomes to figure that out. Say, for example, a while back, this is very early in the development of AI, I think it was at MIT, if I'm not wrong, that the researchers over there developed an AI to distinguish between wolves and dogs, and this thing became extremely good at what it was doing until they actually looked deeper and tried to figure out exactly what the nodal weightages were. And they figured out the reason why it was so good was because it wasn't looking at the actual features of the animal itself, it was looking at the background. If the
Ah,
background was a forest, then it was a wolf,
yeah, yeah,
right?
yeah,
So
yeah.
you can sort of figure that out. Digital systems, without a doubt, are able to identify correlations and causations between different variables far better than humans can. Question
Right.
is, will they be able to identify the same correlations and causations as we are? Now, say, for example, you're talking about the AlphaGo program, the move it made in game two. That one was unprecedented, but simply because we didn't do anything like that. We didn't know how it was working until we actually took a look into it, delved into it. As we go further through the evolution of neural networks, it'll become harder and harder for us to understand how things work. It's almost approaching the mind of God. It's a unknowable kind of concept. So that is an image that's going on right there. Would you agree or disagree with that? How would you perceive that?
Yeah, I think that here you're kind of getting into the realm of some comments that I prepared to talk about AGI and ASI, right? Artificial general intelligence and artificial super intelligence, right? And what some of the risks there are. So let me touch on those two topics because I think they'll get to the answer to your question. Um, one of the big questions right now is, have we achieved AGI, artificial general intelligence? And the problem is that there's no agreed upon definition of artificial general intelligence. Now we're in the realm of, conjecture and opinion. Everybody has different opinions and so on. In my opinion, having vast amounts of knowledge and applying patterns derived from training data to reason and solve, although extremely impressive, doesn't mean intelligence, right? It means it's very, very capable. And like you said, in some cases, it's very hard to decipher. How is it doing this? What is it actually doing to get the right answer? Like the example that you gave. But it doesn't mean that it's come up with a more creative way of doing it that we don't understand. It's just really based on the patterns that it got through its learning. Even the reasoning models, work that way. I mean, in some very contained areas, there is some levels of creativity, like write me a poem, for example. You might say, oh, well, that's creative, but it's still relying on the patterns and so on. You could say that there's some emergent creativity there. But while models today can remix existing knowledge in novel ways, true adaptability and creativity and innovation are really unfamiliar domains and remain a human strength. All right. Can these models work their way through a problem if they haven't been trained on the data that you need in order to solve that problem? If you take a human who has had no survival training and you put them in the woods, chances are they'll find innovative ways and get resourceful at finding ways to survive. I mean, maybe not every human. I mean, unfortunately, there have been people that have not survived in the wilderness, but there have been people that have survived, for days and uh, covering themselves with leaves to stay warm, for example, and finding dew on leaves in order to drink water and things like that. And that it means that what we have in terms of our intelligence is adaptability, creativity, and innovation. And those are hallmarks of intelligence that current models lack, except for maybe some very, small emergent behaviors that we see, like I said, write me a poem and so on. Now, to get to your question, we really need to move into the realm of ASI, artificial superintelligence. And will we ever get there? Now we're in the realm of philosophy, right? We're beyond opinion now and talking about philosophy. Now, artificial superintelligence comes after artificial general intelligence. AGI is as intelligent as a human. ASI, it's more intelligent than a human, right? And here's some interesting things to consider. There's something called recursive self-improvement, and there's a lot of research being done on this. In fact, the people from DeepMind just disclosed a work that they're doing on a system called Alpha Evolve, which is able to analyze itself. The model is able to analyze itself and come up with ways to improve its own performance and write the code, okay, to improve its own performance. And in doing that, for example, it optimized a matrix multiply algorithm that had stood for decades, right? So, it actually did a better job in order to improve its own performance, right? Now, at some point, will this lead to the model autonomously doing this? Saying, oh, let me analyze myself. Oh, I could improve in this way or that way. Let me write the code and rebuild myself, okay, or add that code to my processing, and the models sort of start taking off, on its own. And again, we're talking philosophy now, right? That's not something that's been witnessed in a lab or anything. It's a question. It's a theoretical question. Would a model be able to do that? There's another development called Absolute Zero Reasoner that came out of in May of this year from Tsinghua University, the Beijing Institute for AI, and Penn State, where the model generates tasks, solves them, and then through self-play, by playing against itself, it learns how to achieve those tasks using reinforcement learning with verifiable results. All right, so very similar to like what we talked about AlphaGo, where it played against itself in a sense. So here it plays against itself until it finds a way to answer or complete that task. All right. Now, what's important about this? Well, first of all, it's perfect. It's applicable to things like math and coding where you can verify the results. All right. So it only works on things where when it gets to the result, you can check to see if that result is actually valid. Right. But what's really significant about this is that these models are learning without training data. This is not supervised training where you give it all this voluminous stuff that's labeled, right? And it goes back and figures it. These are creating tasks, solving those tasks, right? Through reinforcement learning with verifiable rewards and coming up with, learning and teaching themselves in ways that have been shown to get improved results over traditional learning methods on different benchmarks, right? So now you start thinking about, okay, you got a model that maybe someday can generate code for itself and improve itself. And then you have a model that can train itself and there's no human in the loop there. Where is this going to go? Right? Where's it going to take you to? Right? And then, of course, there's whether quantum computing can be applied. I'm not going to get into that. That's too long a discussion. But, whether that could actually speed up the ability for these models to do more of what I just described and more training, right? Because there's a lot of potential. There may be potential, right, for that to be a good fit. We don't know yet. Now, the thing is that if these models begin to explore concepts or theories, no matter what they're about, it could be about theoretical mathematics, or it could be about the structure of the universe, right? That those conceptualizations are so advanced they cannot be expressed in human language. Human language is too limited, right, to express those concepts. In fact, models today, and this is already happening with some models, um, they develop their own notation, okay? And when the researchers go in and look at the model, it's, typically they write in English, all the steps that they're going to take, or, in natural language, I should say, all the steps that they're going to take, and you can follow the path. For some of these models, in certain cases, they've generated their own notation to sort of keep tabs of what they're doing, which is more efficient for the models to understand and work with than using natural language, natural human language, right? So we're already seeing some emergent behavior in that regard, where the model's doing something. If you look inside, you can't figure it out, right? Because it's not it's not in a language that you can understand. But if these, models that are getting us to artificial super intelligence, all right, ASI, are starting to deal with advanced concepts that even can't even be expressed in human language, all right, then, where are we, right? Do we lose control, right? And maybe they're coming up with theories and concepts that are verifiable. For example, if they come up with predictions about, what you expect to see in the universe, and you look at the data from the Hubble and James Webb and radio telescopes, and you know what? It matches, all right? What they're predicting is exactly what we're seeing, but we don't understand why we're seeing that. The model does, right? But we don't understand why, because our concept of the expanding universe doesn't match the data, and that's already a case in astrophysics, where we're seeing data from these telescopes that, it's difficult to decipher given our current understanding of the way that the universe evolved. So, at that point, what do you do? Where do you draw the line? All right. And I think Geoffrey Hinton, who, is a Canadian and British citizen, worked at U of T. He had a lot of, a lot of influence in developing neural networks, backpropagation at U of T, with some other, leaders in the industry and in AI. He was quoted, and I've heard this quote many times before, but even as recently as February 2025, he said, "How many examples do we have where a less intelligent entity controls a more intelligent entity?" All right. He said, "There are very few. Evolution has worked hard to let a baby influence its mother, but that's the only instance I can think of." Right. So if we are the less intelligent entity, and these models are the more intelligent entity, and we can't control them, do we pull the plug? Or, all right, because it'd be a shame to not have that power and that capability to advance us further as a civilization, as a species, right? Maybe to solve problems with climate change, to solve problems in medicine, to cure disease, to solve a number of problems. It'd be a shame to give that up. So does this mean that these possible outcomes really underscore the importance of developing robust governance and alignment strategies to make sure that these models don't go off on their own and remain within the boundaries of what we want them to do, right? And I think that's one of the key questions. That's why it's so important that, even in the regulatory efforts that are being looked into, by different legislation and proposed legislation, it's all about alignment, explainability, and transparency. Alignment means the model is not going to do something that goes against our values. So if I ask the model, how do I build a bomb? It's going to say, sorry, I can't tell you that, right? That's alignment, an example of alignment. And explainability and transparency is understanding, how did you get to that answer? What data did you use? What data were you trained on? What reasoning path did you follow, right? And if we don't have that, if we don't build that into these models going forward, then we're going to have that problem of, you know, things happening that we fully don't understand and that we can't control, right?
So the future debate essentially will be a trade-off between human comprehension and the benefits that we could possibly reap from it.
Exactly.
Oh,
Exactly. Yeah.
that is a rather grim image to think about.
Yeah. You can look at it both ways, right? It's either grim
Hmm,
and say, oh my God, humanity's doomed, right? Or if we do it right, and we put in all the proper boundaries and controls and guardrails and all of that,
hmm,
it could be an amazing development in the history of mankind. It could take us to levels that we've never dreamed of in terms of,
hmm,
discoveries that we can make and benefits to mankind. Now, in the wrong hands, in the hands of a bad actor, it could
hmm.
also lead to very destructive uses. It was like nuclear power and the atomic bomb, right?
Right, yeah.
The same thing. You could use it for a lot of good purposes, even medical purposes, or you could use it to make bombs, right? So
Hmm,
hopefully, as a civilization around the world, we'll use it for the right purposes and put
all
the
right.
right guardrails in place.
But then if we're going down the path of, oh, sorry, am I muted? No. Okay. If we're going down the path of comparing this with the advent of nuclear energy and harnessing it, I think we can just say that at most we can just delay that transition. We can't completely circumnavigate it. It's going to happen sooner or later, one way or another.
What's going to happen? That it's going to fall into the wrong hands,
No,
or?
no, no, no. That ASI will eventually happen.
Oh, yeah. I mean, I think AGI. Um, when I say we haven't achieved it, I think that most experts in the field, I read a lot of newsletters and articles and watch a lot of videos from the leading minds in AI. And I haven't heard one of them say yet that we've achieved AGI, but I've heard many say that we're not that far from it, that maybe within the next couple of years or so we'll achieve AGI.
Hmm,
Right? But it depends on how you define AGI because there's no clear definition, there's no consistent definition of AGI in the industry. If it really means matching human intelligence with the adaptability and creativity that entails, all
hmm,
right, then maybe it's a little further off. It depends on the definition. But I think that, from what we're seeing, we might be able to achieve AGI. Now,
hmm,
whether we can achieve super intelligence, like I said, that's a philosophical question. And exactly, what that means to us is something that we'll have to monitor and understand as it evolves. I think that's still,
hmm,
quite a ways off. It's
hmm.
not going to happen overnight.
I'd like to regress at this point and sort of talk about the distinction between um, human intelligence and artificial intelligence. Are we even talking about the same type of intelligence in the whole, or are we talking about two separate different things? Say, for example, when we're talking about human intelligence, what it really boils down to is the ability to make decisions based on a very limited data set. Are we talking in equivalent terms of artificial intelligence, or are we talking about something else entirely?
Yeah, I think, when you say that, what you're really talking about is like the example that I gave of, having somebody who did not get survival training figure out how to survive in
Mm,
the wilderness, right? So very limited data set. They didn't get survival training. So
mm,
they're there, they're faced with a problem they've never seen before, and they have to come up, they have to adapt. They have to adapt what they know to that problem, right? That's something that I don't believe, again, opinion, right, in terms of AGI, I don't believe that the current models, AI models, are capable of doing that to the extent that humans can, right?
mm,
That they can adapt. What they have is a lot of knowledge and they have a lot of understanding of patterns, or, I hate to use the word understanding because it implies like
mm,
intelligence, right? But they have a lot of uh, captured information about patterns that you can apply to that knowledge and so on. And they're amazing at giving you back answers and giving you back information. But if you put them in a situation for which they haven't been trained, for which they haven't been fed the knowledge, and they haven't developed those patterns, would they be able to adapt and innovate and be
mm,
creative, right? And I think, generally, the opinion is, no, we're not there yet. And that's a difference between when you look at a model, an AI model versus a human. I think the human is able to take that step further in terms of adaptability, creativity, and innovation
Mm,
that the models have not yet achieved. Now, will they
right.
achieve that? And at that point, do you call them intelligent? Right? A lot of questions. I think it depends on how we define AGI, how we
Mm,
define intelligence. And then let's not even get into the notion of consciousness and self-awareness. That's a whole nother topic, that where you really get into philosophy, and there are a lot of people with different opinions, a lot of
mm.
very expert thinkers in those fields, that may have different opinions on that.
Yeah, you do see a semblance of consciousness. Say, for example, if you're using Gen AI tools and you give it a simple prompt, you will see it thinking through it and saying that, okay, the user wants me to do this. And you're like, what do you mean, me?
Yeah. Well, you know what? And this is something that people have told me, wow, it sounds human,
Hmm.
right? And why is that? Well, what have we trained it on? Right? We've trained it on books that we humans have written.
Written,
We've
right.
trained it on articles, on content on the internet. We've trained it on all of these things that we've written. And
Hmm.
it's adapted basically our way of communicating, our
Hmm.
style of responding and talking back, if you will, right? So
Hmm.
yeah, it sounds human because we've trained it to act like a human.
Like a human.
But
Hmm.
it doesn't mean they have that level of self-awareness. When they say me or I, they're not really necessarily talking
Right.
about themselves as an entity,
Hmm.
right? They're just kind of using the way that they've been trained by us,
Hmm.
to talk to us the way that we talk to ourselves, right?
Right.
Yeah.
So that would be an example of me failing the Turing test.
I'm sorry?
That would be an example of me failing the Turing test. Thinking of the Gen AI tool as an individual.
Right. Yeah.
Okay, so you did mention that AI has gone through, it's nothing new, it's been around for a while, the concept at the very least, and it's gone through a whole series of essentially new winters where people sort of had a huge uptake and then everyone just suddenly forgot about it. Why now? What's going on right now that has caused such
Yeah.
exponential growth? I mean, say for example, um, when you're talking about AI, um, look at Deep Blue, for example. It was revolutionary in its time. The very concept that if a computer could beat a human at chess was something, well, out of fiction. But then when it did
Mhm.
happen, immediately almost the perception changed, and people were like, well, if a machine can do it, then it's no longer artificial intelligence. And
Mhm.
I remember this one philosopher, I can't remember the name of that person, but they did say that. A computer beating a person at chess is like a forklift beating a person at a weightlifting competition. So why now? Why all of a
Yeah.
sudden are we seeing this rise?
Well, why did we have those winters and
Mm,
why is it different now, right?
mm,
Um, so and this is why I was so intent on trying to give you that mental model of a neural network and the deep learning and how it works, and this back propagation, resetting the weights and learning from that process and so on. We didn't have that in Deep Blue, right? We didn't have that in Jeeves, although I don't think Jeeves, caused a winter. Um, but those other technologies were very narrow and they weren't generalizable. And it led to the disillusionment. They didn't have the legs, right, to carry forward. And then there were other, developments. I mean, the notion of neural networks have been around for a long time. There's people that defined and built something called perceptrons, right? Many, many years ago. But what was lacking? What was lacking were things like GPUs. GPUs, which are graphics processing units that were introduced by NVIDIA, they're highly parallelizable machines. And what do you need when you think about all these neurons, right? And propagating all this data through all these layers of neurons and doing all these weighted averages and dot products, matrix dot product. What do you need? You need a lot of parallelizability, right? And when GPUs were introduced, they actually enabled these neural networks to function in a way that they could never have functioned within a reasonable amount of time, on a standard CPU or even a mainframe or supercomputer, unless it had these kinds of parallelizable technologies like GPUs. So that, I think, really enabled a lot of the development of neural networks. There was also, for a long time, there was a lack of training data. And actually, there was a woman named Fei Li, who's a professor at Stanford University, that developed a data set called ImageNet with over 14 million labeled images. So you know those cats and dogs we talked about, right? It's that kind of thing that also enabled neural networks to get trained, right, and to develop. And in fact, ImageNet enabled Geoffrey Hinton when he was at U of T, together with Alex Skrichevsky and Ilya Sutskever, who are, Ilya has gone on to do amazing things also in the world of AI. Um, it enabled them to build an image classification deep learning model that they called AlexNet. And they were using like early, GPUs that outperformed every other classification approach. And as a consequence, it was a turning point for the notion of neural networks having the promise to take us further, having the legs, all right, to take us further in AI without another winter, all right, that they would not cause disillusionment. And look what's happened, right? We have the transformer architecture, the attention mechanism, generative AI, the ability not only to generate images now, but videos. It's really advancing because the underlying technology and the underlying concepts have the legs to take us forward. All right. That's what's different, in my opinion, than what we saw in the past, where you got a really great result like Deep Blue, but it wasn't generalizable and you couldn't take it further, right? Whereas these things now are going off in a ton of different directions. They can write code, they can, write content, copy. They can generate videos. Now they can generate videos with voice. Okay, I think Google just in I/O in their conference just announced that. VO, I think is the name of it, if I recall correctly.
With
You
the
know,
live
we,
language
we
translation.
yeah, we have
Yeah.
these amazingly photorealistic images of people talking, and you have the voice and the background audio and everything, completely built in. All right. So does the technology have the legs? In my opinion, it has demonstrated that, and I think it can still take us, further in new additional developments like agentic AI, for example, which is the next stage that's coming, is where not only will you chat with an AI model and it gives you a response, but you'll ask it to do stuff for you, and it'll have the ability to use tools, like the web and databases and CRMs and Excel spreadsheets and all this sort of stuff to actually carry those tasks out for you, right? So you can tell it, hey, make me a reservation at this restaurant on that date for two people at 7:30.
Mm,
And it'll go out and make the reservation. If there's an online reservation system, it'll just execute, it'll just do it. And it'll come back, your reservation is made. If they don't
mm,
have an online reservation system, it'll call the restaurant and talk to the person and make the reservation, or it'll come back to you and say, there's no availability here, the times that are available. Do you want me to call back with, one of these, right? So, this is what we're seeing emerging now, and you can have multiple agents collaborating to perform things like supply chain management. Okay, in manufacturing and a number of different areas where you have agents really communicating with one another that are running the logistics of a supply
mm,
chain. All right, and you control them. They're autonomous, right? But you control them, and they can carry out the tasks instead of just here's a prompt, give me an answer. It's here's an instruction, perform that task for me, right? And I mean, we could get into it would take a long time to talk about all of the different ways that agents can, be applied in different industries and so on. But I think agentic AI over the next year or two or three, maybe through 2027, I think you have to keep an eye on that and see the developments that are coming there, and they're already emerging,
mm,
right?
mm.
I think they hold a lot of promise for doing some really highly productive things.
Right, right. So, Al, we have a question from Latoya, and
Yeah.
this is a question you see often in the world out there. You say, do you foresee AI replacing jobs? Now, the common answer to this question is that AI won't replace people, but people who know how to use AI will replace people. And that is certainly true as of the state today. But do you think that is going to continue with the advent of agentic AI?
Yeah, I think that agentic AI agents still need to be managed, and
Mm,
they're basically, think of AI agents as personal assistants,
mm,
right? And this is where I get to this notion of AI augmented professionals, right? And that is the quote that you just read, that
mm,
you know uh, uh, people who don't use AI are the ones that are going to be replaced by people who do use AI, right?
mm,
So I think what's important at this stage, at least, is to embrace AI. And as a professional, ask yourself, how can I augment my professional capabilities with AI? All right. So, for example, if I'm, as a professional, I'm doing market research, right, for my company. And if I need to understand the market dynamics in certain areas and who the competitors are and all of that, if I had a research assistant
mm,
working with me, all right. And already, things like deep research and all of that provide incredible ability to get you information that would allow you to complete a research analysis
mm,
in far shorter amount of time than it would take without the use of AI technology, right? So it's not that you want to hand over the responsibility to AI and say, here, here's a task, just do it. And when you give me back the results, I'll just submit them.
mm,
That's not the way that I think it's going to be successful for people. And that would be replacing people, right? If you take the person out of the loop and just say, oh, that thing can do it, right? These agents, I think, are going to be more assistants to professionals who can work with them and get
mm,
more done. An agent can be trained or taught to do the rote work that you maybe do in your job so that you can spend more time doing higher level thinking or addressing, higher level problems or breaking new ground as opposed to, oh, I don't have time for that because I have to do this, 5 times a day I have to do this. I mean,
mm,
one example I can give you is, there's a lot of talk about doctors getting burned out because of all the patient records that they have to fill out every day
mm,
after the consultations. There's so much paperwork, especially
mm,
in family medicine and so on. Now, imagine a doctor that has a safe and secure AI agent sitting in on the consultation, right? And afterwards, the AI agent gives the doctor, not only gives the doctor the summary of everything, but fills out all the forms and
mm,
says, here it is, sign off on it, review it and sign off on it or modify it if I made mistakes, right? Imagine, how much time it would save that doctor. And what are they going to do with that time? Well, hopefully, they're going to spend more time with me, right, in the consultation, or they're going to spend more time doing research and learning about new treatment plans and new medical discoveries, new conditions that they need to learn about. They're going to spend more time improving as a doctor in their profession because they have this agent doing the
mm.
rote work for them,
Right.
right? And I think that's one of the ways that we need to think about it, right?
Mm.
Yeah.
So we need to get AI essentially to do the grunt work. What will change is what counts as grunt work.
I'm sorry, say that again.
We need AI agents essentially to take over grunt work for us, so that we're
Yeah,
left with the higher cognitive areas. But then, what counts as grunt work? That definition will change over time as well.
that'll change over time as well, of
Right.
course. Yeah.
Mm. Awesome. So for someone who wants to become an AI optimized professional, what's the path for them
Well, I
to
think
be an AI?
yeah, I mean, there may be training programs that you can take. There's a lot of really good video content, these days talking about AI. I think we're going to be seeing a lot more content for upskilling and reskilling that involve teaching people how to use AI more effectively.
Hmm,
There are a lot of AI products out there, ChatGPT, there's, Llama from Meta, there's Google Gemini, there's a number of different AI systems and products. Anthropic has Claude. If you're a programmer, I mean, they're sort of moving in that direction of being really, really capable, for programming. Uh, I'd say engage with it, right? A
hmm,
lot of these applications are free and you can go in and play around with them. Some of them require, a subscription fee. Right now, one of the ones that I use is like 20 US a month that I pay in order to get access to some of the more advanced features. But if you can, and you don't have to sign up for a whole year, you can sign up, for a few months and then cancel
hmm,
it, when you're done. But I would say look for these upskilling and reskilling programs that are emerging. Um, uh, get in and play with these AI systems, understand, how they work, and how they can work for you and what they can do for you and how you can augment yourself as a professional by making use of these AI. Remember, don't relegate what you do to AI. All
hmm,
right. If you have to write a paper, don't say to the AI, could you write me a paper on this topic and then you're done. All right. In that case, you're taking yourself out of the loop. You're taking yourself
hmm,
out of the job, right? The way that you, I think, want to approach it is say, okay, I'm going to make the first draft and I'm going to give it to the AI to give me a critique. And then I'm going to maybe look at the recommendations and say, okay, some of these make sense. I'm going to put them in and I'm going to evolve and iterate on that paper with the AI system
hmm,
as my co-author, if you will, as my assistant, my editor, somebody who can review my paper and tell me, well, you could say this more clearly if you rephrase it this way, right? And
hmm,
those tools are already, available. And you can use AI in that way. So there's a way that as long as you use it to sort of critique your work and help you advance and improve your work, as opposed to just giving it and relegating it off to the AI system. That's not, in my opinion, the best way that you can engage with AI, right? Now, there are also news feeds that you can sign up for. And maybe, Ishan, what I can do is, I can give you uh, some of the links and so on to some of these news feeds. If you're
that would be
really
spectacular.
interested,
Yes.
yeah, if you're really interested in the topic, then you probably would want to sign up to some of these feeds and be kept abreast of what are the latest developments, what's coming out from the providers of AI technologies, what do these things do? There's a lot of videos, and the people that do the news feeds also have a number of videos that they review the new releases of these AI products. And it depends, to what degree you want to get into it. If you really wanted to understand things like the structure of neural networks, backpropagation, autoencoders, variable autoencoders, all of this technology way beyond what I talked about. There's an MIT lecture series on YouTube.
Hmm,
There's another set of videos from an organization called Three Blue, One Brown that you can also find on YouTube, which has excellent videos to kind of give you that kind of insight into how all of this stuff works. So, well, a lot of it depends really on the degree to which you want to know how it works versus how can I use it? All
hmm.
right. And I think as a professional, the more important question is how can I use it and where can I learn how to use it better and so on.
Awesome.
Yeah.
We have one more question from Nina. Nina says, "Hi Al, thanks for the great talk. How has the role of product evolved with the integration of AI into digital products? What new skills and mindsets have become essential for those in product? And how do you ensure transparency and user trust when designing products with AI?"
Yeah. So when you're, there's First of all, you need to look at how can I use AI in the process of product development. So we do market research, and you have to write specifications and all of that. You can use AI internally, to do some of that work. But then there's the question of integrating AI into a product, right? And there you really have to make sure that you're looking at safe AI. Basically, you don't want to put in capabilities that maybe are hallucinating or providing incorrect data. But you have to give the user a warning, right? If you're giving them access to an AI capability, um, just like all the AI systems do, they say, "Hey, AI can make mistakes. You should check this," right? But there's a lot of ways in which you can integrate AI to improve your product, in ways that the user would have to validate, some of the work. Like for example, if you're somebody who is submitting something to the product, and the AI is maybe summarizing, or the AI is extracting information from that submission and putting that into a profile or into a form. You don't just let the AI do that and then push it out, right? You do it and then you tell the user, can you verify this? All right, can you check all of the stuff that our system was able to extract from your submission, and make sure that it's all right, before you hit submit. Okay, and generally you want them to check every single item in that regard, right? So, and the other thing, and this is there's always a bit of a tension here, is you want to improve your product with AI, but you don't want to do it. You don't want to jump the gun and do it before you're using a system that can be relied upon, that's transparent, that has good alignment and so on. But always, in my opinion, you want to give the user the ability to verify and check and approve, what's coming from the AI system before they go ahead and use it.
Awesome. Al, thank you so much. I mean, this conversation can go on forever, but we're already well over the time limit we had set for this session. So I think it would be great if we could schedule another one sometime soon, because our users, and particularly me, would be very interested to hear your opinions, particularly as we go on towards agentic AI. So
Mhm.
thank you, Al, for your insights. They have been very illuminating. Thank you, everyone, for joining in. We will be having another session in a couple of weeks, so please do sign up for that. But other than that, take care, stay safe, and well, see you the
Thank
next
you
time
very
around.
much.